Hopefully this is set up to record correctly. We'll find out when we actually try to replay the recording. But if that doesn't work out, I can always give this talk again. So, hello, I think most of you know me at this point. For the purposes of the recording and posterity, David Varvel, Director of Pivotal Labs Singapore. I'm going to give a really brief introduction to microservice planning. This is a talk that I've given before when we were doing workshops on microservices and breaking a monolith into microservices and things like that. This is not going to be an exhaustive talk on how to break a monolith into microservices or how to deploy microservices or a lot of the technical topics like circuit breaker patterns and things like that around microservices. Instead, this is going to be a very brief introduction to what I consider some of the very core concepts that you need to understand in order to successfully implement microservices in your organization. The first things are understanding at its core level what microservices are and what they're good for. So I'm going to give you a spoiler alert right now. I'm actually going to tell you the end of the talk right now. Okay. And what I'm going to be leading up to is I'm going to be presenting the idea that the most important thing you can do when planning microservices in your organization is name your teams. That's highly counterintuitive, which is why I'm saying it right now, so that you can keep that in mind and keep it churning in the background as we go through this. So what are microservices? This is a widely accepted definition. Microservices are independently evolvable and autonomously deployable services that govern their own state and incorporate resiliency patterns. There's a few things I want to focus on here. Independently evolvable, these are units of code that you can change independently. They can even have different technologies, be built using different technologies, like Golang or Ruby or Java. They're not necessarily connected. Autonomously deployable and govern their own state. These are things where you can deploy one microservice and you don't have to deploy other microservices at the same time. You can deploy them on an ad hoc basis as you see fit. And they manage their own state. That's what makes them often autonomously deployable, is that I'm not impacting the state of another microservice when I change the database schema, for example, to support my microservice. Resiliency patterns, that's very important when you're building distributed systems. You have a lot of network calls. Network calls tend to fail. You have a lot more moving parts, and so you need to make these things in a more robust fashion. I'm only going to focus really here on the autonomously deployable piece, because that's actually why most organizations want to adopt microservices. People often say, well, I have the problem of I have one team that wants to make a change, and I don't want to break what another team is doing, right? That's usually the problem statement. Is I don't want what one developer is doing break the system for all my other developers. Let's talk about the classic monolith when you don't have microservices, right? And the challenge of independent deployability. Let's dive into that independently deployable problem for a moment. So this is the monolith. You started banging out code and it starts doing cool things, and so you start adding more code, and then as features grow and as the project evolves, you just end up this big pile of code, which is a big monolith of code. And the problem is when the monolith gets so big that you want to have a lot of people working on it. It's too big for just 1 or 2 or even 8 people to continue to evolve this monolith to meet the needs of your project, meet the needs of your product. So you start spinning up additional teams. You have, start with team A, and then you have team B and team C, and you need all these people in order to deliver all of the features and functionality that this product requires. Well, this becomes a big problem when you start checking changes in, and these different teams start checking in changes, right? Because this team is going to check in a change, want to deploy it, but they then need to start coordinating with what team B is doing and team C is doing, and it ends up looking a lot like this, where you have this is Scrum, by the way, but everybody's looking for who has the deployment token. I've worked in environments where there was a stuffed animal, and you couldn't deploy unless you had the stuffed animal. And that way you didn't get 2 people trying to deploy things at the same time and breaking each other's changes. It's very problematic. And it becomes virtually impossible when you're dealing with large multi-team structures. You look at a large project we dealt with, like there's a large automobile company that has a blue oval, and have geographically distributed teams checking into the same code base. It produced a lot of problems with deployability. And when can you deploy? Who can make changes? What are the impacts of those changes on other teams? So you start wanting to segment your product into different pieces that these different teams can make changes to autonomously. And this is a much nicer situation here, because team A can change their piece of the product without impacting team B, and nobody's fighting for the ball anymore. Everybody gets their own ball. It's a very different sport. So if you look at it from that lens, microservices, one of the prime values of microservices, that allows you to restructure your teams. It allows your teams to be decoupled from each other. There's other benefits, like the technology heterogeneity, whatever that word is, where you can use different technologies. There are new patterns that you can introduce, but having the ability to scale your product easily across a multitude of teams is, in my opinion, the big win with microservices. Now I'm gonna talk about something only vaguely related for a little bit. Talk about domain-driven design. So, what is domain-driven design? Before I give a definition of domain-driven design, let's just look at code for a moment. Line of code. This is a class. It has a function. Function takes 2 arguments. Actually takes in, and then it performs an operation using the objects that are passed in. So what does this code do? Why does this code exist? Is this good code? Does it do what it's supposed to do? I don't know. How about this? This is exactly the same code, but with names given to these things. Boat controls. You want to change the heading of a boat, and so you pass in a boat object and a location object that is the destination. You can set the heading of the boat to go to the destination. I think this is pretty good code. We can have a discussion about, are these the right objects to be passing around? Is this exactly how we want to structure this thing? Because we can now think about boats and controls and destinations and things like that. But from a computer's perspective, it's exactly the same code. And actually, the compiler will strip out these symbols. So this is more about a mental model that the mental model of the programmers in talking about the code than the code itself. I'm going to tell you a little story from my own life about mental models. In America, we have a lot of land, and that allows you to build excessively large houses. And most of those houses, of course, you spread out, so you need a car in order to get anywhere. And so you build a garage to put the car in. Usually the garage is also excessively large. And so you end up putting a lot of boxes and just stuff in the garage. It becomes a storage unit, not just for your car, but also your Christmas ornaments and board games and whatever junk you have lying around for sports or what have you. And most garages end up looking kind of like this. And that's okay, because it's the garage. You don't live there. You don't entertain guests there. You don't eat there. It's just, all you do is store stuff in there and maybe park your car. So I moved from San Francisco to Washington, D.C. at one point. And in San Francisco, we had a house that had a garage, and we used it as storage, much like this, because the garage was a lot bigger than the small car that we had, and so we had a lot of stuff. And then we moved to Washington, D.C., and we moved into an apartment that didn't have a garage. So we had just a ton of boxes of stuff, all those Christmas ornaments and sports equipment and things that we'd accumulated over the years and just stuffed in the garage. Now they were in our living space. And it's like, okay, what do we do with these boxes? Well, fortunately, we had an extra room. We had an extra bedroom. And we just put all of the extra boxes of camping equipment and holiday stuff into that extra room, and we called it the garage. And it was kind of a joke because, hey, it's our garage where we stick all this stuff. And of course, we want to turn it into an actual livable space over time. So we'll slowly deal with this, with all of these boxes, and slowly evolve it into a livable space. And then 6 months later, we realized we had made no progress in changing the garage into a livable space. It still was just stuffed with boxes, and you couldn't do anything there, and it was effectively a useless storage room. Now, this is what a garage looks like. This is what a bedroom looks like, right? When I say bedroom, probably think of something like this. I mean, maybe you're not going to pick that color for the bedspread, but when I use the word garage, I think of this, and when I use the word bedroom, I think of this. So my wife and I started calling that room the spare bedroom. And when you look at this, when you look at the room and you say, "Oh, this is the garage and it's full of boxes," it's like, well, of course it's full of boxes. It doesn't defy your expectations at all. You look at the spare bedroom and it's full of boxes, like, "Ooh, I need to do something about those boxes." So we started calling it the spare bedroom, and within a couple months, all the boxes were gone. There was a bed in there, and it was a spare bedroom where we could have guests. Names really matter. Having a mental model for something really matters because it helps guide you and tell you when something is wrong. If you have a mental model and something doesn't match your mental model, you're going to want to fix it. You're either going to adjust your mental model, which is actually often difficult, or you're going to want to change something to fit your mental model. So names identify a mental model. And actually, this is one of the cool things about language. One of the magic tricks as a human I can do is I can say some words and put a mental model that's in my head in your head. It's really cool. So that sharing of a mental model is absolutely critical. It's one thing we do all the time in every aspect of our lives. Now, there's a quote from George Fox: all models are wrong, but some are useful. So having a perfectly precise mental model is good, and there's always going to be a conversation around these mental models, and the conversation is often the really productive part. Now let's talk about domains. So this is from Eric Evans, who effectively created domain-driven design, encapsulated a lot of the conversations that were happening in the late 90s, early 2000s. And he says every software program relates to some activity or interest of the user, and the subject area where you're using this program is the domain of the software. You know, software has a job. What does it do? And in which activities is it being used? So you take the idea of a domain, a problem domain, and a mental model, and you end up with a domain model. Here is my mental model about this domain that the software is operating in. And a large part of working on a team and working on a high-performance effective team is making sure that you all have a shared mental model of what this software is supposed to be doing. What problem is it supposed to be solving? Are we building the right things? Are we structuring our code in the right way? You can only have that conversation productively if you can have a good conversation about the domain and the mental model of how your software fits in that domain. That's one of the reasons we do pair rotation, is to help unify people's mental model around the problem domain and around the software itself. So let's go back to our team structure here. Say we name these teams. You know, if you go back to team A, team B, team C, what's the problem domain here? What should that team be building? What should this microservice do? Really hard to have a conversation about that. If you name your team, this is, say you're running a travel service. You could have the booking team, the payments team, the rewards team. It's really clear and obvious to stakeholders, to people on the team, to people on other teams, what domain these people are playing in. And you can develop a mental model of, oh, here's how payments relate to bookings. Here's how I expect payments to relate to bookings. And people within bookings can have a mental model of, here's how I expect bookings to work. This is what we call a bounded context in domain-driven design. So having this domain model, this shared mental model, and you can decide, as a programmer on this team, as a PM on this team, as a designer on this team, as a manager who's structuring teams, here's what the booking team should be working on, and here's how it should relate to what's happening with the payments team. Here's Conway's Law. This is something we talk about a lot. Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. The classic example that I like is the US Army and the US Navy decided to work on a software project together, and they ended up building a system that was an Army module and a Navy module and a command module up at the top to control both of them. We've seen this over and over again in our own projects, in companies. You know, you set up a team working on one thing and a team working on another thing, and the code base starts to reflect that. And so one of the things you can do This is called the reverse Conway maneuver. You take your monolith and you want to break it into microservices. Well, what microservices should you break it into? Don't start by looking at the code. Start by thinking about the problems that the code is supposed to solve. Think about the mental model. Think about the bounded contexts that you want inside that code base. And then if you name your teams, say you have the booking team, the payments team, the rewards team, all of a sudden everybody's going to have a mental model about what belongs to the booking team, what belongs to the payments team. And what you'll see is the code will naturally start to split apart into a booking service, a payment service, a reward service. And if you set the right expectations and if you have shared mental models about how those things interact, then the API calls between these things become much more natural and much more obvious. So how do I know which teams I should have? This is the hard part. So say we all agree on this. Okay, great. Which teams should I actually have working on this? Which teams do I want? Because once I start crafting teams and naming teams, the code will start reflecting the team structures that I have created. And the naming of those teams is critically important. I worked in an organization that at one point that allowed teams to name themselves. And so you would get teams with names like Runs on Bacon, which everybody thinks is hilarious, but makes it very difficult to interact with that team because you say, it's not intuitive. Should this code belong to the Runs on Bacon team? I don't know. I mean, maybe everything should run on bacon. So, but then you're back to a monolith. So not having clear naming between these teams and not setting those expectations actually led to a lot of difficulty and confusion from not only a team interaction standpoint, but also an architectural standpoint. Like, what do you give to those people? So this is event storming. This is an exercise that is designed to help with this problem, where you first need to identify what does your system do? What does your product do in general? What is the entire problem domain that you're trying to tackle? And I'm assuming that your problem domain is too big for just one team, but let's get the whole thing out and put it all up in sticky notes on a big wall and say, okay, what does the system do? Now, are there natural groupings between these things? And if you start seeing clusters of functionality, you can say, oh, this is probably a nice bounded context that we can draw, and we can build a team around it and start building microservices around it. One caution I think we always have to give is that this is a continuous conversation. As the needs of your product evolves, as the needs of your organization evolve, as technology evolves, you're going to want to revisit this. And the structures that you have today may not be the structures that you want tomorrow. So it's advisable to be continuously evaluating, do I actually have the right bounded context? Do I have the right teams? Is the code telling me that I have problems with that I haven't perfectly captured the right bounded contexts? Or am I seeing opportunities to unify things, or are there other indicators that we should restructure? So one of the things that technical management can do and architectural planners for these systems can do is continually revisit, do we have the right teams in place? Do we have the right names for things? Do we have the right zones of control for these teams so that they can go and build their own correct mental models inside those zones? And that's basically it. That's what I feel to be an important level set before people dive headfirst into microservices. It's very easy to get immediately sucked into the technical components, and how do I deal with network segmentation, and how do I deal with security and authentication, and all these other really interesting service discovery, really interesting technical issues. But I think it's really important to have this conversation with everybody that's going to be involved with these microservices, so that we have a shared mental model about what's important when planning out these microservices. And that's it. Thank you very much. And at this point, I'm happy to take any questions you might have.
So usually when our clients have a monolithic application, they already have one giant database, a certain application. So if we break down the application to microservices, what do we do? What approach can we take to break down the database?
That's a good question. Often people recognize that they have an issue with scalability of the code first, and they say, okay, let's create separate code systems, or maybe you have systems that want to share data. For some reason, you spin up a new system that wants to get information from another system. And the easiest thing to do, and probably the worst thing to do, is directly access the database tables for that system. But if you look at the definition of microservice controls its own state, right? So by definition, if you have a shared database, you do not have microservices. And those things are not independently evolvable because you're not completely in control of your own state. So you lose all of the benefits of microservices being independently deployable and independently evolvable. So it's not a question of should we split the database, it's a question of how fast can we do it and how do we do it, right? And that's the first step with this conversation is always making sure that we're on the same page, that we need to split apart the database and that these things need to have their own state. Once you get agreement and alignment on that, you can come up with a strategy for splitting out the database. It might be that you are able to completely decouple database tables and still have people hitting maybe the same quote-unquote database, the same Oracle or Postgres or MySQL system, but they're accessing completely separate tables, and then it's just a simple database migration. Another strategy that is employable is you can create an API layer and start adjusting all of the systems that are directly accessing the database to hit a thin API layer that serves up that data from the database. And then that abstraction layer allows you to shift and move how that data is actually physically represented on the database layer. And then you can evolve that API independently. So those are a couple strategies, but I think the first conversation of making sure that everybody is on the same page about the need to decouple from the database, decouple the databases, that's the most important thing.
I actually have another question.
Sure.
So let's say, take the example of I have a booking system, I have a payment system, and the two system somehow, let's say I make a payment, there has to be a booking associated. How do we enforce that? How do we enforce that the booking has to be there when I make a payment? Otherwise, anybody can tamper the payment database, and then I might be paying for nothing.
Yeah, yeah. This is the hard part, because the fact is that these microservices, if they're completely independent, then they just be completely independent products, right? Often they do have you have some level of interaction between them. So this is where the actual architecture planning of how do these microservices interact becomes very important. Your first most obvious choice is an API call. Like I'm going to do this processing, and then I'm going to make a call to this other microservice to get say the payment needs booking information. I'm going to the payment service will make a call to the bookings. Yes, payment service will be called the booking service. if that's not performant enough for some reason, you may introduce some caching layer. That's where something like a gemfire may come in handy. And then you have to have a conversation about what is the source of truth. Can your domain handle eventual consistency? Those kinds of questions. One important thing to consider is that the code, if you find that a piece of your architecture is challenging, that should prompt a conversation about, do we actually have the right domains carved up? If you're finding that getting that booking information for your payment service all the time is a real bottleneck, or that it's breaking a lot, or it's hard to manage for some reason, then maybe you don't really have a payment and a booking service. Maybe you have a trip service or something that actually unifies some of these concepts. So you should always be listening for problems that your current structure is giving you, and use that as a trigger to say, do we actually have the right bounded contexts in our system? Because maybe we need to revisit those.
What about really clean having like the booking, payments, and the other service? What about things that fall in between the cracks?
I think that's the conversation, and that's where you get these really protracted conversations. I think event storming is really useful for establishing those boundaries and laying everything out on the table, saying, what is the entirety of what this system, or at least the section of the system, what is the entirety of what it does? And then by definition, nothing is falling through the cracks because it's all on the table. And then you can draw boundaries around groupings and have a decision, okay, who owns what? If it's not immediately clear, if you don't have agreement on the mental model and the naming of these domain contexts, and it isn't immediately obvious when you take a new feature which team it should go to, which domain it belongs in, then either your mental model isn't good enough, you need to have a further conversation about how this fits into the existing model, or you need to revisit the model. And again, it's a prompt for this conversation about, are we actually grouping things the right way? Are things named correctly? I threw up those names. I think there's a lot of devil in the details, to Yifeng's point. What happens when you need to call need to call booking data for payments and things like that. I don't think you can get away from the actual implementation details and individual features at any point. And we should always be listening for, does it feel like something is just thrown in or falls between the cracks? Because if something doesn't clearly and obviously fit within its named box, then that should be a trigger for a conversation of like, do we need to change names? Do we need to think about new boxes? Does that address it?
So in a typical database design model, we have payment table, we have booking, and so customers. So we have primary key, foreign key, standard database. So when you put microservice around it, so either you can have separate schema for this certain table, or you can have one schema with separate table. Payment table is Excel by payment service. So how do you, are you suggesting so we put a foreign key primary key relationship here, or we just ignore any database? Because that has advantage and disadvantage.
So I think it's very risky to be relying on foreign key primary key relationships between microservices, because the idea here is that you are in complete control of your own state. And if I have a foreign key dependence on another table, then I am no longer in complete control of my own state, right? If that table is being managed by another service. These are the trade-offs.
Because if you ask a database architect, so he will say, okay, it's a completely new thing. So
Right, exactly. And this is why that alignment is like, you say, well, you shouldn't be sharing the database anymore, like to a lot of classic DBAs who want your entire problem domain mapped out in a third normal form on, in your database tables. This is anathema to that. This is the opposite of that.
for them, like let's say when you CRM system, for them CRM is the whole domain. So everything is one domain for them.
Exactly. And the microservices say that you shouldn't do that. that you are no longer in control of your destiny as a microservice if you cannot completely control your state and the state that matters to you. So microservice design forces a conversation about how you're utilizing databases. It's worth noting that I believe Netflix is pretty much internally standardized on Cassandra, which is column-oriented, when you do not get a lot of those really nice, RDBMS type features, because they don't use them. They don't need them. And they're more interested in having rock solid, consistent read and write performance at scale.
I think because there is no transaction support also, then you have to take care of everything.
Exactly. So microservices are not free by any stretch, and they are not a good solution for every problem. I think that's something to make clear here. You're introducing a whole lot of complexity. You're introducing the possibility of network partitions. I've never seen a function call in memory fail. Like, in my entire career, I've never seen one of those go bad. I cannot count the number of API calls I've seen fail. So by introducing an API call, changing something from an in-memory, in-process communication to a network communication, you're making it orders of magnitude slower and less reliable. That's not always a great choice. Sometimes that's not what you want. So you have to consider, why are we building microservices? What are these microservices intended to do? And what benefit are we hoping to derive from microservices? The big benefit of that people usually get out of microservices is independent deployability. Having the ability to have different teams operating on these things, and not have teams in that really nasty scrum of trying to grab the ball. In order to solve that problem, you're going to have to make choices where you lose some of the niceness of a monolith talking to a nicely laid out relational database.
How would you, I have a question around, let's say you have two existing services, not necessarily one model, but you have two things that are, as you said, like separate technologies. But you find out that your bounded context, there's actually like three, and one is like a sandwich between the two or something. How would you recommend like splitting that out between like which technology you would move that bounded context to, or maybe remove it entirely, or redo that whole thing?
Yeah, so those are your options.
Yeah.
Yeah, it kind of depends, man. I'm going to give that bullshit consulting answer that says it really depends. It depends on what technologies, it depends on what domains. I think there isn't a magical answer for everybody in every problem domain of how you should lay out these services and how you should evolve those services. It all seems to be extremely context dependent. Some of the things you should definitely be considering are things like performance SLAs, other metrics like how rapidly can you evolve code. Like how hard is it to change something? Is a technology supported? Is another driving factor for investing or not investing in a technology. Where do people have expertise? There's all sorts of all sorts of considerations. And the hard conversations are when you have an existing system and you realize you need to re-segment it in some way. Like I said, with the example of having these different named teams in the monolith, it's not like it just magically happens and like splitting that code magically happens. It's not like the code refactoring fairies come in overnight and do it for you. Like, there's going to be a lot of really hard conversations that those teams are going to have about, okay, how do we split this? How do we actually get to independently deployable components? What is the moment that we do that? And I think there's examples in the office of like we talked about Sun Electric. You know, we're building a new thing. We have an old system. How do we balance which parts of the system we carve out? Which ones do we do first? There's a lot of good there is a lot of good literature on that, and we have a lot of in-house expertise with the OutTX team, people who have actually gotten in the weeds with those kinds of problems. So if you're interested in some interesting case studies, I'm sure we could dig that up.
Previously we are using we were using the monolithics, right? There's some features like transaction control, right, which were very easy. You can commit everything or roll back everything, right?
Yep.
So we introduce more complex in the microservices world. But sometimes those requirements are still valid, right? So how we address this kind of questions or concerns? Any patterns, recommendations?
I think you always need to think about how much eventual consistency you can live with. It's worth noting that Google's this is probably a few years out of date at this point, but last time I looked at it, Google had a scheduler system for their internal container management, for their internal data center management. They had various systems that would basically decide what was running where and relocate processes if it needed to. All of the stuff that something like Diego or other internal Cloud Foundry components do. That piece was monolithic. And I think they built that piece as a monolith because they needed that consistency. Like trying to have a distributed source of truth on what is running where was just not performant and not really practical for them. It's also worth noting that most of the time, scalability is not a reason to put in microservices. Because most monoliths are horizontally scalable from the code perspective, and a modern database can handle a lot of transactions per second. Like if you're exceeding 10,000 transactions per second, yeah, you're in some pretty exotic territory. Like 99% of software does not require those kinds of scalability requirements. So if you have something that is a source of truth, like financial data that needs to have that transaction support, maybe you should just have a service that does that. And that is consistent. And if you have something that's going to modify an account balance, it talks to that service, and that service controls that and has that transaction support. It's also worth noting that each microservice, if you have your own database, you have control over your own transactions. So you just need to identify which things are sources of truth. And when a microservice fails, say you need to do a rollback, distributed rollback starts to get very complex very quickly. So you should always be asking the question every time I make a network call, what do I do when that network call fails? And it's fractal. Every service should be having that conversation. Go is actually really good at this because it forces you to answer that question. Every time you make a network call, it's like, okay, and then your error is. So that's part of the tax in implementing microservices. Is all of a sudden you have to start considering all your failure modes because you're going to have a lot more failure modes, and those things are going to be a lot more complex. Does that?
I believe a lot of communication to handle the error and also a big problem in microservices.
Yes.
That's straightforward.
Yeah, I think microservice. One of the things that people probably don't consider enough when building microservices is error handling and failure modes, because distributed systems can fail in really weird and unpredictable ways.
Do you currently have a garage?
No. I don't have a car either, so. All right. Thank you very much, everybody.